All right, so this is section 6.4, and it is all about logarithmic equations. And so the last section was all about solving exponential equations. This is going to be solving equations that have logs in them. All right, so the first kind of idea that we're going to talk about is if you have log of something equal to a log of something, and those two logs have the same base. In this case, the base is not written, so it's base 10. But if they have the same base, then what we can conclude is that the inside of the two logs, whatever you're taking the log of, those two things have to be equal. So in this case, x has to be equal to 4 in order for those two logs to be equal to each other. Same thing is happening over here with this equation. You have log base 10 of 2x equals log base 10 of 6. And those two logs are the same. They're both base 10. And so since you have a log equal to a log, you can say the inside of the log, or what you're taking the log of, is equal to what you're taking the log of on the other side. So this would be 2x equals 6 when x would be equal to 3. And so here's kind of like the theorem. It says if log of m equals log of n, then the insides m and n, whatever is on the inside, has to be equal. All right, so we have some more examples of using this property. Sorry, I can't get this one here yet. I'm gonna make some adjustments. All right. Okay, so the next one says 14 log of 84x equals log base 84 of 49. And so what's happening with this problem is you do have two logs. They are the same. But right now, this log has a 14 in front of it, and so that's going to throw off being able to use the last property directly in saying that the inside of the logs are equal to each other. But there is a rule out there that we have talked about lots of times that says, hey, if there's a number in front of a log, what can you do? You can put that back into the power. So what we can say, get my hand out of the way, we can say log of 84, log base 84 of x to the power of 14 is equal to log base 84 of 49. And now we have two logs that are the same. They have the same base, and they're equal to each other. So now we can go ahead and say x to the 14th is equal to 49. And then it says, the question says, leave your answer in exact form. So as we go to solve this, we're not going to use our calculator and do any decimals or anything. But you can get rid of the 14th power by taking the 14th root. So this would be the 14th root of 49. And yes, 14th roots exist. They're just not very common, right? We just don't talk about them a bunch. And so here is your solution for x. All right, here's another one. We have log base 72 of x plus 6. That's a plus. Plus log base 72 of x is equal to 1. And this one, we're still going to use that property, and we're still going to have two logs equal to each other, but we have to do some combining, condensing, and some changing of some forms first. So the first thing I notice is log base 72 of something plus log base 72 of something, and you can put that into one log base 72, and on the inside of that log, you take those two things and you multiply them. Remember, that's one of those properties as well. So this would be x and x plus 6 being multiplied. So I'm going to say x squared plus 6x. Hopefully you're okay with multiplying those at this point. And then that's currently equal to 1. Well, there's a couple ways to think about this. This is actually a property as well, that if you have the log, any base, and it's equal to 1, that what's on the inside has to match what the base was. So this right here has to be 72 in order for that property to work. Log base 72 of 72 is equal to 1. Another way you could think about this is you could think about changing this 1 into a logarithm. So 1 would be log base 72 of 72, the same kind of general property we've been talking about. So whether you change the 1 to the log base 72 of 72, or if you just know that this has to be 72 in order for it to be that 1, either one is fine. So what we can say is x squared plus 6x has to equal 72. All right, and we're going to solve this quadratic. Remember, when you go to solve a quadratic, something that has an x squared, you can factor, quadratic formula, complete the square. Nobody wants to complete the square, but you could. And so I'm going to go ahead and factor. So I'm going to move this over so it's set equal to 0. And I'm looking for two numbers that multiply to be a negative 72 and add up to be a positive 6. And the numbers are actually 12 and 6. 12 times 6 is 72. And then to get positive 6, the negative goes with the 6 there. So the factors are x plus 12 and x minus 6 equal to 0. And so your solutions are x equals negative 12 and x equals 6. All right, there is one more thing we have to talk about before we leave this problem, and it didn't come up in any of the other ones, but it's something that you always just kind of have to be aware of. There is a restriction in the domain of the log function. So if you remember, we talked about the domains of the logarithms as we were graphing them, and we noticed that it was never in the negatives. X didn't have any values in the negatives. And so the restriction is, and kind of the rule is you can't take the log of a negative number. That's not allowed. You're not able to do that. There's no actual value there. If you try to throw it in your calculator, it's going to say there's an error. So it falls under the same rules/issues with domain. You can't divide by 0. You can't take the square root or the even root of a negative number, and you cannot take the log of a negative number. So those are kind of 3 things that, in terms of domain, you absolutely positively cannot do. So we just have to check these 2 values if they make the log, if it ends up being the log of a negative number. So you should go back to your original before you do anything. Go back to your original and plug in both negative 12 and 6 into both of these x's and see if you get a negative. So if you put negative 12 in here, negative 12 plus 6 is negative 6, and that would be the log of a negative number, and so that would not work. So x cannot be negative 12. It is what we call extraneous. We didn't make a mistake in solving or anything. It's just we get a solution at the end that doesn't actually work because of domain issues. And then you should check the other one. If you plug in 6, 6 plus 6 is 12, and that's a positive number, so you're okay. If you plug in 6 right here, you're only going to have a 6, and that's positive, so that's okay as well. So 6 is a solution, but negative 12 is not. So as you're working on these logarithmic equations, if you put in a solution and it gives you partial credit, it might be because one of the solutions you put in actually made it extraneous, and you would want to go back and check that. All right, so we have a few more to solve here. So we have log base 2 of x plus 6 minus log base 2, and I know you can't see it, but it does say x minus 9 is equal to 4. And so we're going to go ahead and solve this. And the first thing we're going to do is we're going to put those 2 logs together because they're both log base 2. So we'll have log base 2. And then on the inside of the log, because there is a subtraction sign between them, they get divided. So x plus 6 is the numerator, x minus 9 is in the denominator, and that will be equal to 4. All right, so from here, you need to change the 4 into a log, or we need to do something in order to kind of get rid of this logarithm. And so another option that I did talk about on the last one is you can just convert to an exponential. That's an option as well. We talked about at the very, very, very beginning when we first addressed exponentials and logarithms. So convert to an exponential. So the cool thing about these problems is there's a lot of ways you can solve them. The bad thing is there's a lot of ways. So there's not just one set thing. You could think about it in a couple different ways if you wanted. So if you convert to an exponential, here's a reminder. It's 2 to the power of 4 will be equal to this. So 2 to the power 4 will be equal to x plus 6 over x minus 9. And from here, you're good to go ahead and just do the algebra and solve. So 2 to the power 4, that is 16. So that's equal to x plus 6 over x minus 9. And then to get rid of the fraction, you're going to do the opposite of the division. And opposite of divide is multiply. And you're going to multiply by whatever is in the denominator. So since x minus 9 is the denominator, you'll multiply by that on both sides. And what will happen over here is they will make a 1 essentially. They're just going to go away. So we're left with x plus 6. And then on this side, you can go ahead and distribute 16x. And I have minus 144. And then from there, it is just a algebra 1 multi-step equation. So you're going to put your x's together, everything else on the other side, and do the division. So you'll have 15x over here. You'll have 150 on this side. And then we'll have x equal to 10. And once you're done, and you get x equals 10, you do need to go back to the original problem and just check to make sure that you don't have a negative. So 10 plus 6 is 16, that's good. 10 minus 9 is 1, that's good. So 10 is the correct solution for this problem. All right, another type of equation to solve. This one we have natural logs. And we're going to solve for h in terms of b. And so what they're saying is they're saying, hey, figure out what h is equal to. And, oh, by the way, there's a b in there. So the b is just going to stay in there. You're just going to do the algebra kind of around the b instead of having an actual value there. So we're solving for h, and the b is just going to kind of float through our problem as we are working on the solving for h. Oh, there's another h right here. I didn't even see it. Ooh, multiple h's. That might make this harder. All right, so let's go ahead and see what we can do here in terms of the fact that there's a ton of natural logs and there's 4 terms and there's just a lot going on. So the first thing is these are natural logs. They're on the same side of the equal sign. They are being subtracted. And so since they're both natural logs, you can put them into one natural log with a division operation because of the subtraction. So it'd be 12 minus 12h all over h. On this side of the natural log, you have, or on this side of the equation, sorry, you have a natural log, but then you also have a term that does not have a natural log, and that's the one with the b in it. But what we can do is we can write this as a natural log. So this would be the natural log of e, because that's equal to 1, to the power of 3b. And that's using one of the properties we talked about kind of in reverse. And so 3b would be the natural log of e to the power of 3b. And it's e because natural log is base e. And this simplifies to just 3b. So you'd have the ln of e to the 3b plus 2 ln of 17. And you can actually do a little bit more to solve here, right? The 2 can go into the power and make that a 17 squared. And because you have 2 natural logs now being added, you can write them as 1 natural log with a multiplication. And so it would be e to the 3b times 17 squared. All right, and we're actually getting a lot closer here. There's still quite a bit of algebra to do, but we've made quite a bit of progress now because looking at this, I see a natural log equal to a natural log. And so those are logs. Natural logs are, they're logs. They have the same base. So we can go ahead and use the property that says that the inside has to be equal to each other. By the way, 17 squared, that's 289, right? So we can go ahead and change that so that this inside of the natural log is equal to this inside of the natural log. All right, and from there you can just work on trying to solve for h. So we're kind of out of the world of natural logs now, and we're just working on getting that h by itself. So the problem is there's two of them. This one's in a denominator, so this is going to be kind of interesting. So you can take this h and get it out of the denominator by timesing by h. So times both sides by h. So this would be 12 minus 12h equals 289 e to the 3b times h. And then because you have two h's, you want to go ahead and put them on the same side. So I'm going to move this 12 over. So we have e to the 3b times h plus 12h. So you get those h's on the same side together because we want to solve for h. So having one on one side, one on the other doesn't really help us out. So what we can do now is we can go ahead and factor out the h, so that instead of having two of them being added, we have one in the front being multiplied by a term. And so that's kind of the trick there, to take multiple h's and turn it into just one h. And then last but not least, you're just going to do the division. So there'll be a 12 on the top, 289 e to the 3b plus 12. So that one's definitely a little bit more interesting because of the fact that there was the 3b at the beginning, and then you have all these natural logs that you're trying to put together, and you ended up with multiple h's that you were trying to solve for. So that one was pretty hefty in the world of, like logarithms and properties, and it wasn't just kind of like a basic solving. There was a lot of like little things that you had to kind of remember along the way. All right, two more for this section. So we have this one. It says solve log base 2 of x plus log base 6 of x equal to 1. And then it says, not just solve, it says write an exact answer in terms of the natural logarithm. And so that's kind of an interesting thing there. Write it in terms of the natural logarithm. So first of all, I noticed that this is log base 2 and log base 6. So that's kind of a bummer, because if they had the same base, I could put them together, right, and make it in one log. But unfortunately, they don't. And so what we can do here is we can do a change of base, just like when we were typing log base 2 of something in our calculator, or log base 6 in our calculator, we can change the base. And so because it wants it in natural logs, we can actually go ahead and change the base of both of these into the natural log. So the first one would become the natural log of x over the natural log of 2. X being the number on the inside, 2 being the base. This next one becomes natural log of x over the natural log of 6. And those are still being added together, and they are still equal to 1. All right. In terms of solving for x here, I noticed that both terms have a natural log of x. So what I can do is I can divide, or I can factor out the natural log of x and have 1 over ln of 2 plus 1 over ln of 6 equal to 1. And let's see, this is ln of x times this. So what you can do is you can go ahead and divide this over. So you can say ln of x would be equal to 1 over 1 ln of 2 plus 1 over ln of 6. And then we're super close to getting that x by itself, since this is a natural log. And we don't have just a natural log. If there's like a natural log in front of this or whatever, we'd be okay. But there's a lot more going on here than just a natural log. And so we're going to go ahead and do the process of converting. So if you don't have a natural log equal to a natural log, and you can use that property, you should convert to an exponential. So we're going to convert it to an exponential. And so natural log is base e. So if you need to write that in there, that's base e. So it'd be e to this power, literally the whole thing. This is the power is equal to x. So it'd be e to the power of 1 over 1 ln of 2 plus 1 ln of 6 is equal to x. And on that converting, then we get what x equals, and we are done. We're good to go from there. That one was quite interesting because we had to use a change of base formula, and then we had to do some algebra in terms of like this middle factoring out the ln of x, and then we had to convert it to an exponential. All right, last question for this section. It says solve the equation for x, give an exact solution, and a 3 decimal approximation. So exact solution first, and that's what they want here is they want to know what numbers go here for the exact solution, and then here we'll put our approximation. All right, so my equation is the ln 9x minus 9 equal to 116. And so I'm solving for x, so I have to get rid of the natural log. I'll have to get rid of the minus 9 and the times by 9. And so in order to get to that natural log, because this is not equal to a natural log, the easiest step is to convert to an exponential. So we've done this a few times now in this section, is convert it to an exponential. And so when we convert, we'll have base e, so it'll be e to the power of 1.6 is equal to the inside, 9x minus 9. So solving for x, you would add 9. So e to the 1.6 plus 9 equals 9x. And then you can divide by 9. So e to the 1.6 plus 9. And when you divide, it's all divided by 9 equal to x. All right, and then this actually falls exactly how you see here. So this would be e to the 1.6 plus 9 divided by 9 equals, and then we're going to have to go ahead and throw this into our calculators. Let me grab that real fast. So I need e, and if you notice on the log and the natural log, the button's right here. This is 10 to a power, and this one's e to a power. And that's because those are the bases that it's log base 10 if nothing's written, and natural log is base e. So the e would be wherever the ln button is on your calculator. So if your ln button's over here or something, the e should be with it. So because it's yellow, we're going to hit second, and then e to the power of 1.6. Whoops. Close your parentheses, and you can say plus 9 right now. And then you should hit enter, and after you hit enter, hit divide by 9. So it takes the entire numerator, the entire answer from the top, and divides it by 9. It says round to 3 decimal places, so the 3 decimal places would be right here after the 0, so it'd be 1.550. So our approximation, 1.550. All right, so that's it for the notes in this section. Go ahead and work through those questions on My Open Math and let me know what I can do to help you.